Explore how tiny microcapsules can teach us about planets, stars, and the fundamental balance of forces in the universe. Imagine a tiny sphere just microns across, balancing forces just like a planet balances gravity and pressure. This is the Microcapsule Universe Analogy. Let's start by understanding what microcapsules are and why they matter. A microcapsule is essentially a microscopic container, a tiny sphere containing liquid surrounded by a thin elastic membrane. These capsules are incredibly small, typically ranging from 1 to 1,000 micrometers in diameter. That's about the width of a human hair or smaller. Here's our microcapsule. It has a radius r, a thin membrane on the outside, and pressurized fluid on the inside. In scientific notation, the radius ranges from 10 to the negative 6 meters to 10 to the negative 3 meters. Three main forces govern the behavior of microcapsules, just like forces govern celestial bodies. The first force is internal pressure. The fluid inside pushes outward on the membrane, trying to expand the capsule. We call this P in, the internal pressure, measured in pascals. Think of internal pressure as arrows pushing outward in all directions from the center, trying to make the capsule expand. The second force is surface tension. The membrane itself resists stretching and tries to minimize surface area. We denote surface tension by gamma, measured in newtons per meter. Surface tension acts like arrows pulling inward along the membrane, trying to shrink the capsule and minimize its surface area. The third force is external pressure from the surrounding fluid, which also pushes inward on the capsule. We call this P external, the pressure of the fluid surrounding our microcapsule. These three forces balance according to a fundamental equation discovered in the early 1800s. The Young-Laplace equation states that the pressure difference equals 2 gamma divided by r. This is the key equation governing microcapsules. But what does this equation actually mean? Let's break it down piece by piece. Delta P represents the pressure jump across the membrane, how much higher the internal pressure is compared to external. The term 2 gamma over r represents the effect of membrane curvature. Smaller radius means higher curvature and larger pressure difference. Here's the key insight. Smaller capsules have higher pressure differences because of their higher curvature. Larger capsules have lower pressure differences. Let's calculate some real numbers to make this concrete. Consider a tiny water droplet in air. Suppose our droplet has a radius of 1 millimeter, which equals 10 to the negative 3 meters. The surface tension of water at room temperature is approximately 0.072 newtons per meter. Now we can calculate the pressure difference across the droplet surface using Young-Laplace. Delta P equals 2 times 0.072 divided by 10 to the negative 3, which gives us 0.144 divided by 0.001. This equals 144 pascals, or about 0.0014 atmospheres. That's a small but measurable pressure difference. To put this in context, atmospheric pressure at sea level is about 101,325 pascals, so our pressure difference is relatively small. Here's an important question. What happens if we make the droplet much smaller? Let's reduce the radius by a factor of 100 and see how the pressure changes. Now our radius is 10 micrometers, or 10 to the negative 5 meters. The pressure difference becomes 14,400 pascals. That's 100 times larger than before. This reveals a fundamental principle. Pressure difference scales inversely with radius. Halve the radius, double the pressure. This graph shows the inverse relationship. As radius decreases, pressure difference increases dramatically in a hyperbolic curve. Now let's make the connection to planets and stars. How are microcapsules like celestial bodies? In a planet or star, gravity pulls matter inward, just like surface tension pulls the membrane inward in a capsule. Internal pressure from hot gas and nuclear reactions pushes outward, resisting gravitational collapse, just like fluid pressure in a capsule. Look at this comparison. Both systems have internal pressure pushing out and an external force pulling in, creating a balance. For the capsule, we have delta P equals 2 gamma over r. For a planet, the pressure gradient is proportional to gm rho over r, where g is the gravitational constant, m is mass, and rho is density. Stars maintain balance through hydrostatic equilibrium, much like microcapsules maintain their shape. In a star, at every point from center to surface, the outward pressure gradient must exactly balance the inward gravitational force. This is expressed as dp doctor equals negative rho g, which equals negative gm of r, times rho over r squared. Here's a crucial question. What happens if this delicate balance breaks down? If internal pressure becomes too large, the star expands and cools, like inflating a balloon. If pressure becomes too small, gravity wins and the star collapses, potentially forming a white dwarf, neutron star, or black hole. These three scenarios show expansion when pressure dominates, balance in equilibrium, and collapse when gravity dominates. Let's apply these concepts to our own sun and calculate some real numbers. The sun has a radius of 6.96 times 10 to the 8 meters, or about 696,000 kilometers. Its mass is 1.989 times 10 to the 30 kilograms, an enormous amount of matter. At the sun's center, pressure reaches about 2.5 times 10 to the 16 pascals, billions of times atmospheric pressure. This immense pressure comes from nuclear fusion reactions and the weight of all the overlying material compressed by gravity. Despite its violence and energy, the sun maintains perfect hydrostatic equilibrium between pressure and gravity. One powerful aspect of this analogy is understanding how different physical quantities scale with size. Here's an important question. How does pressure scale with radius in microcapsules versus astronomical objects? For microcapsules, pressure scales as 1 over r, inverse linear scaling. For self-gravitating objects like planets, pressure also scales approximately as 1 over r for objects of similar density. Remarkably, both systems show this inverse scaling with size, making the analogy mathematically meaningful. This graph shows how both capsules and planets follow similar inverse scaling laws, though with different proportionality constants. Let's examine the energy involved in creating and maintaining these structures. In a microcapsule, the dominant energy is surface energy stored in the stretched membrane. Surface energy equals gamma times 4 pi r squared. It scales with surface area. For a planet or star, gravitational binding energy is the dominant form, representing how much energy would be needed to disperse all the mass to infinity. Gravitational binding energy is approximately negative gm squared over r. An interesting question. How do these two types of energy scale differently with size? Surface energy scales as r squared, growing with size, while gravitational energy scales as r to the negative 1, increasing as objects get smaller. Stability is crucial. When are these systems stable against perturbations? A microcapsule is stable when surface tension is strong enough to resist the internal pressure trying to burst it. The stability condition is that gamma must be greater than delta P times R divided by 2. A star is stable when the pressure gradient at each point exactly balances the gravitational force. What physical changes can make either system become unstable? For capsules, instability occurs when the membrane weakens or internal pressure becomes too high. For stars, instability occurs when nuclear fuel depletes, reducing internal pressure and allowing gravitational collapse. The transition from stable to unstable involves crossing a critical threshold where restoring forces can no longer maintain equilibrium. These concepts aren't just theoretical, they have real practical applications. Microcapsules are widely used in medicine for controlled drug delivery, releasing medication slowly over time. By understanding pressure relationships, scientists can design capsules that rupture precisely where needed in the body. In astrophysics, these same principles help us predict stellar evolution, supernova explosions, and black hole formation. Both pharmaceutical science and astrophysics benefit from this fundamental understanding of force balance in spherical systems. For those ready to go deeper, the Virial theorem connects kinetic and potential energy in bound systems. The Virial theorem states that twice the kinetic energy plus potential energy equals 0 for stable bound systems. Here K represents total kinetic energy of all particles, and U represents total potential energy, primarily gravitational for stars. This can be rewritten as kinetic energy equals negative 1/2 the potential energy. In stars, kinetic energy comes from the random thermal motion of particles, essentially temperature. The Virial theorem beautifully connects temperature and pressure to gravitational binding, explaining why stars are hot. Here's a fascinating question. Why does a star actually heat up as it contracts? As gravitational potential energy becomes more negative during contraction, kinetic energy must increase to maintain virial balance. Contraction increases the magnitude of U, which increases K, which increases temperature. This is why collapsing gas clouds heat up. Let's directly compare numerical values between microcapsules and astronomical objects. This comparison table shows that microcapsules have radii from micrometers to millimeters, and pressures in the hundreds to hundreds of thousands of pascals. The Sun, by contrast, has a radius of 700 million meters and central pressure of 2.5 times 10 to the 16 pascals. Enormously different scales, but similar physics. Despite vastly different scales spanning more than 14 orders of magnitude, both systems follow remarkably similar physical principles. It's essential to understand where this analogy breaks down and what it doesn't capture. The first major difference is the nature of the restoring force, elastic membrane tension versus gravitational attraction. Second, stars have an active energy source from nuclear fusion, while microcapsules are passive structures. Third, stars evolve over billions of years through nuclear fuel consumption, while capsules are essentially static unless perturbed. Fourth, quantum mechanics becomes crucial for very dense stars like white dwarfs and neutron stars, with no analog in classical capsules. This comparison highlights the limitations of the analogy, particularly regarding the role of quantum mechanics in stellar physics.